Okay. Let's get started. It's my pleasure to introduce our colleague. Hello. Perfect. Yep. Good. So let's get started. It's my pleasure to introduce our colleague, Professor Gowtham Kaki, who is an assistant professor of computer science in our department. Professor Kaki has been working on topics on formal verification, programming languages, and program analysis. And his work has received multiple awards from places like Google and Amazon. Today, he is going to talk about affordable formal methods for practical distributed system. Please join me in welcoming Professor Kaki.
Thank you for the warm welcome, Ashutosh and folks. So before I start, one announcement. So those of you who are here for the Colloquium class, a sign-in sheet will be passed, so you have to sign in on it. So your course manager asked me to make this announcement. So yeah, please do sign in on your sign-in sheet for the students who are here. Okay, so good afternoon, folks. So the last time I gave a talk in this classroom was 5 years ago in 2020 February, and a few days later, the world shut down. So my turn has come again. So welcome back. So yeah, today I'm going to talk about the research that my students and I have been doing on what I call as affordable formal verification for practical distributed systems. Okay, so I'll start with the basics, the little bit of background, right? So for most of us in this room are programmers and from the microarchitecture perspective, our mental model of a computer, it comes from the von Neumann model, right? So in a von Neumann machine, we have a central processing unit, CPU, where all the computation is done. And then the data for the computation, as well as the instructions that drive the computation, come from a separate memory unit, right? So that's why the von Neumann machine is usually called a stored program computer, because the program is actually stored. We use the same hardware to access both the data and the computation, right? And we have we have complete control over the contents that flow between the memory and the CPU. We assume that the data access is somewhat instantaneous. So although the von Neumann model itself does not include a clock, I'm going to talk about. Oh, okay.
Yes, yeah.
Let me. Oh, okay. Yeah.
Screen sharing is paused.
Screen sharing is paused. Why is that?
Okay.
Thank you.
Can this be?
Changes again. Maybe you
Not-
share the whole screen.
Yeah, let me stop the share and share the whole desktop.
Get to see if else is there in the.
Hi. For you.
Said it paused again up there.
Yeah, click on this.
I am not able to click on the show.
If you can click OK, maybe that's.
Right. Stop share. Share screen. Desktop 1. Share. Let's say. Yeah, I'm sharing the entire desktop. So let's see. Does it work? Okay, wonderful. Okay, great. So yeah, sorry about the interruption. So yeah, so we have this concept of a stored program computer, right, where the program is stored along with the data in the memory. And we assume that we have complete control over the contents that flow between the memory unit and the control and the CPU, right? So although the von Neumann model itself does not come with the notion of a clock, I'm going to talk about performance today. So I'm going to include a clock in the picture, right? So a clock synchronizes all the activity across various circuits in CPU. So we can measure the latency of operations in terms of clock cycles. For example, the memory access latency is few hundreds of clock cycles, right? The raw memory access latency. Okay, so over the years, there was a hierarchy of caches that were introduced between the memory unit and the control unit to exploit the locality of reference and increase or decrease the memory access latency. So we now have the effective memory access latency of around tens of clock cycles, right? So the actual number is not important, but the key takeaway is the control and data flow is pretty much instantaneous, right? So when we program our applications on top of our computers, so we're actually not worried about the latency of control flow or data flow, right? So this includes even the modern applications. So for example, if you're, let's say, writing a simple neural network that classifies and missed images, it is still a stored program on your local machine. It does computation as per the von Neumann model and so on, right? Okay, but what about the applications that we have come to be known as cloud applications, right? So do you think Amazon.com is a stored program in some computer in Seattle? Or is Instagram like some program on some computer in San Francisco? Not really, right? So these programs sort of execute, or these applications execute as programs over hundreds, if not thousands of computers, or tens of thousands of computers across the world, right? So their data is distributed. Their control is also sort of distributed. So the data is replicated across various machines across the globe. The control sort of flows between various machines. So in order, and the network that connects these different machines is actually, it's sort of an unreliable network, right? So sometimes the distributed network system is overlaid on top of an internet as a virtual private network. But most often, it's simply the internet that sort of connects your nodes, right? So, and the fastest we can communicate between these nodes is via speed of light. It's the ultimate speed limit of the universe. From the inertial frame of reference, the speed of light is quite fast. But if you're looking at it from the perspective of clock cycles, right, it's not that much, right? So the speed of light is around 6 inches per clock cycle. So before your memory access concludes from your main memory, a beam of light would have barely crossed this building, right? So the key takeaway from that is that the control and data flow is not actually instantaneous, right? So you actually do feel the latency of control flow and data flow, right? The second important aspect of a distributed system is that the network on which it is built, internet usually, is a shared network. It's an open and shared network. So it has two major implications. So the first is because you're sharing the network with multiple traffic flows, the performance is not predictable. There can be congestion, packet drops, or sometimes even network partitions. The other implication is that the system is not isolated, right? So you actually, the data flow, which was previously private to your own application, is now visible to whoever is actually observing on the internet, right? So the system is not entirely isolated. So these are the two sort of major implications of building this sort of a large distributed system connected via public network, right? So a distributed system may not look like exactly like this. So these are distributed systems as well. So you can have a 5G cellular network where user agents are communicating over a cellular network via base stations and cellular backbone. Or you can have a fleet of unmanned aerial vehicles which can communicate amongst themselves via control tower and so on, right? So the key point is the communication between these various agents is unreliable and vulnerable, right? And the control and data flow is not instantaneous. So these are the three key things that sort of define a distributed system, right? Okay, so the question now is, how do we program these massive distributed systems to ensure fail-safe operation and resilience against adversarial attacks, right? So this is the question that has been motivating programming languages and formal methods research for quite some time now, right? And there have been a string of successes recently, right? So formal methods, for example, has been widely adopted at Amazon Web Services. They develop a language called P, wherein they actually prototype their distributed systems blueprints and verify them before they actually develop the actual implementations. Microsoft has Project Everest, which has been going on for 9 years, where they developed verified cryptographic libraries that are actually deployed in production. On the government end, DoD agencies such as DARPA are quite enthusiastic about adopting formal methods. So DARPA a few years ago had a program called HACMS, High Assurance Cyber Mechanical Systems, I guess. Cyber military systems. Thank you, thanks, Shiro. Yeah, so HACMS, which has been quite successful. So there, what the performance did was they were able to translate, or they're able to build a verified operating system on top of an unmanned aerial vehicle, and so that the red team weren't able to hack into UAV despite having access for it for like a week or so, right? Even having access to the source code. Okay, so yeah, NASA has been adopting formal methods for quite some time. So here I cite a work of them using formal methods to essentially verify their rover and a lander for Mars. And the newest kids on the block are these blockchain applications that support smart contracts. So the idea is smart contracts sort of are responsible for transferring huge sums of money across different accounts. So they better be invulnerable, right? So they better not be vulnerable to reentrancy hacks and so on. So that's the motivation for them to adopt this sort of formal methods, right? But however, if you observe, so these are the string of successes are quite motivating for formal methods researchers. However, these are mostly sort of high-tech organizations, right? What we think of as high-tech organizations with with access to computational resources and expertise, right? So the adoption of formal methods across the general community, the general programming community, has been quite low. There have been quite many impediments to widespread adoption, and it is quite significant at this point because the ongoing trend in software development is to adapt towards more decentralized architectures. So blockchains and federated social networks are an example. So we want to support programmers in the development of this new sort of software, the new application architectures. So we want widespread adoption of all methods, right? So these are the impediments to widespread adoption of all methods. So one is poor scalability, right? So formal verification is mostly confined to abstract models because verifying real distributed systems requires enormous computational resources and a lot of manual effort. The generality is also insufficient because most of formal verification has been, especially in the context of distributed systems, has focused on safety properties. But if you look at decentralized applications such as blockchains and federated social networks, so the security is the most critical aspect. The privacy of users and security are this critical aspect. There aren't many formal methods or formal techniques that can sort of address those problems. The last is the steep learning curve that is generally associated with applying formal verification because users typically have to write specifications, invariants, and proofs. These are not something that programmers generally write in their day job. So formal methods, to be widely applicable, have to work with what's available in terms of unit tests, assert statements, and natural language documentation, and so on, right? So these are sort of what I see as main pain points for the widespread adoption of formal methods, especially in the distributed programming, right? So my research at CU has focused primarily on developing programming abstractions and automated reasoning techniques to bring affordable formal verification to practical distributed systems, right? So I believe this can be done by developing novel programming abstractions and reasoning techniques. So that's what the focus of my research has been. And my mission is to basically make the formal verification sort of accessible to a mainstream application developer and make them productive in distributed application development. So I'm supported by several smart students, highly motivated students here in achieving this mission. So here are some of them. I'm going to talk about their work as we go along. Right? Okay. So today's talk, I'm going to focus on 3 different strands of my research, addressing essentially the 3 impediments that I've identified in the adoption of formal methods in distributed programming, right? So the first is addressing the scalability aspect. Basically, how do we improve scalability so that we can take formal verification from models of systems, distributed systems, to the actual implementations. The second is improving the generality of formal methods so that more and more properties can actually be verified, right? Reliably verified. Number 3 is improving usability of formal verification so that not just the experts or people who have PhDs in formal methods, but also the programmers who can actually use these things in practice. Right? So these are the 3 broad sort of strands of the research broad strands that sort of guide my research. I'm going to focus on these 3 aspects.
It's okay. Go.
Is that a question? Okay. Any questions at this point? Okay, I'll move on. So first, the first part I'm going to cover is basically the research that we have been doing on improving the scalability of formal verification, especially focused on distributed systems, right? So how do you go from verifying models of distributed systems to actual implementations? So the contributors, so Nick is the primary one who's driving this research. Prashant has contributed, and I've been collaborating with Evan on this. So I'm going to focus on a couple of papers in this area. So the tools that have resulted from this work are available publicly. They are open sourced. So I'm going to talk about them in a while, right? First, I'm going to set a little bit of stage, right? So I've introduced von Neumann model a while ago, right? But from the programming perspective, right, we don't always think in terms of microarchitecture when writing programs, right? We have high-level programming languages that sort of abstract away the sort of memory contents and all of those things, so that we can think of essentially programming as going across states, right? As a state machine. So basically, a computer is a state machine that sort of moves across states, and you sort of drive it to the state that you want to compute, right? So that's the high-level abstraction of a computer that we use in our daily life in programming. So the corresponding abstraction for a distributed system, right, can be obtained by generalizing a state machine, right? We call it a replicated state machine, an RSM abstraction, right? So this is an abstraction that was introduced in 1970s by Nancy Lynch, Leslie Lamport, and others. So the idea is, regardless of the low-level aspects of the distributed system, there should be a high-level abstraction that sort of abstracts away these network faults and all of those things and supports a state machine style of programming, right? A replicated state machine style of programming. So state machine is actually replicated, and programmers should be able to program against that thing. So that was the main dream, the dream that was motivating the distributed systems researchers back in 70s and 80s, right? So let's look at RSM abstraction a little bit closely, right? So I'll explain it with an example, right? So it's basically a state machine which is replicated across 2 different locations. So let's say the current state of the machine is S3, and Alice does an operation on S3, right? You get a new state S4, and the key is the state is instantaneously reflected on the other replicas of the machine as well, right? So that's the abstraction that replicated state machine aspires to offer, right? So next, a while later, Bob comes along and does an operation on a different machine at state S4. So Bob should be able to read the latest state S4, perform an operation, basically extend it with a new state S5, right? So your state sort of progresses linearly, right, in time. So what we get is essentially just a regular state machine, but just sort of replicated at various locations, right? So we call it, just to emphasize the linear nature of progression, we call it a strongly consistent replicated state machine, or block RSM. They just, Lynch and Lamport used to just call it as RSM, but we want to distinguish between this sort of state machines and the other state machines. So we're going to call them as strongly consistent replicated state machines. So block RSM. Okay. How can we realize the block RSM in practice? Well, in practice, things are not so simple, right? So Alice does an operation to node A. So there's a new state S4, but the network might go down. And so you may not be able to, the state S4 may never actually be reflected in the second replica. So when Bob comes along, and so Bob reads the latest state as S3, so does their operation, so you end up with the new state S4 prime, right? So what we have is divergence of states, right? So this is not the replicated state machine abstraction that was originally conceived, right? But if you just let the things be in practice, so this is what you'd end up with, the divergence of states, right? Which is actually quite bad. Okay, so what researchers did is, the one way to prevent this divergence, so they came up with the ways to prevent this divergence, right? So the key idea is, if the machines in the system can somehow sort of come to an agreement on what the next state is for a given operation, that is, they can come to a consensus on what the next state of an operation is, then you can sort of do that operation and say that that is going to be the next state of the system, right? So for example, Alice submits an operation, right? So the machine sort of think for a while. So they sort of come together and sort of perform a round of consensus, right? And they arrive at a consensus that the next state is actually S4. So they update the state to be S4, right? And next, Bob comes along, does their operation. And so there'll be consensus across the system of machines and decide the next state is actually S5, right? So this is what we call as a consensus-driven replicated state machine development, right? So the key insight is like distributed systems when composed with consensus would actually give us the block RSM abstraction that I've been talking about, right? Okay, so there have been several consensus protocols that have been proposed over many, many years to achieve consensus, right? Why are there so many? Well, systems do evolve over time. There are new trade-offs that show up, and you want new algorithms or new protocols that sort of are more efficient for that sort of trade-off, right? So generally speaking, there are two broad classes of consensus protocols that are widely used. There are others as well, but among the widely used ones, you see Paxos, which was introduced by Lamport in '98, and Raft, which is supposed to be the more understandable version of Paxos, applied to log replication, right? So these are consensus protocols, right? So yeah, they do implement consensus on top of a distributed system. However, consensus between among the machines of a large distributed system requires several rounds of communication, right? It's basically coordination intensive, and coordination is quite expensive in practice, right? So these distributed protocols are actually not that scalable. They're not quite scalable. But more importantly, we call them as essentially not being available, right? So what do we mean by availability? Well, let's say, for example, in this machine, somehow the two of the machines become unreachable, right? And Bob comes and tries to do an operation on a single available machine, the machine that is actually responding. The machine still cannot progress because it does not have what we call as a quorum, right? I'll explain what exactly a quorum is later. So it doesn't have a quorum to actually proceed and make progress, right? So it is impossible to have consensus in this world unless sort of network's partition heals and you sort of have the machines back. Right? So this is what Lamport meant when he said that a distributed system is one in which a failure of a computer you didn't even know existed can render your own computer unusable, right? So here Bob's computer is actually still working, but he still can't use it because the other systems are not functioning, right? The other sort of downside is these are the consensus protocols are some of the most complicated protocols out there. So they're quite error prone, right? So the implementations are, because there are several rounds of communication, they have to deal with several faults. The implementations are quite complex, and therefore formal verification actually guaranteeing that their correctness is quite high, right? So the key questions that we want to focus on is, can we avoid strong consistency or consensus in practice? If not, can we make formal verification sort of scale to the actual implementations, right? So if you want to avoid strong consistency, what are the guarantees we can give, and how to formally verify those guarantees? These are the two key questions in this in this context. So I'll focus on the first question first, right? So let's go back and revisit our earlier slide on divergence, right? So we have Alice and Bob contacting different machines, and we have different states. So we said, well, this is bad. There is, states have diverged. So consensus protocols actually let you sort of preempt this thing from happening, right? But let's say we sort of let it happen, right? And if you focus on it, so this is how the divergence looks like, right? Somehow we let it happen, and if we have a means of merging these diverged states, right, then somehow we can repair the system, right? We can somehow, despite transient divergence, we can sort of get the states together again and get all the replicas or all the machines to agree on a final state, right? So this is called eventual convergence. So we don't have consensus here because there is a transient divergent state, but eventually we have convergence, right? So if you have a machine or replicated state machine with this sort of an abstraction where there can be transient divergent states, but eventual convergence, we call it as eventually consistent replicated state machine. So this is a term that I coined. So it's just I want to denote it as the diamond RSM, so that to denote the eventual aspect of the replicated state machine. So it's So this is as opposed to the strongly consistent replicated state machine, right? Okay, so we do have, so how is the diamond RSM useful in practice? So we have seen diamond RSM in practice. All of you have seen it, right? So a Git version control system is a great example of an eventually consistent replicated state machine, right? Because you do have, sort of, for example, a master branch, and you might clone a bug fix branch onto your machine. Your friend might clone a feature branch on their machine, and they might make their own changes. So there is temporary divergence between your friend and you, but finally you can sort of merge these changes into a single sort of a final version, right? So there is eventual convergence, right? So if you want to do this in general, right? So we want to replicate this merge, semantics for objects of any arbitrary type, right? So we have objects of any type, and there should be a function that should be able to merge sort of two concurrent states of versions of the object, given the common ancestor version of that object, right? If only we can do that, right? Then we can sort of use this as a means, the implementation of the object extended with the merge function, right? To sort of have this system, a diamond RSM system, that eventually converges to a single state, right? So it's not as great as a consensus system, but it is still something, right? You could use it to implement, for example, counters that can eventually converge to a single value. For example, the YouTube view counter and so on, right? So in an example of a merge function, for example, for the set data type, is one where you might want to, when there are two concurrent versions and their common ancestor version, you might want to have elements that are common in all three versions, plus the newly added elements in set S1 and the newly added elements in set S2, right? So as simple as that, you have a merge function for set. So we have, if we take the standard library implementation of a set data type and extend it with the merge function, we get what we call as a set mergeable replicated data type, which is essentially a data type which you can use as a distributed data type. It is replicated, and because you've defined a merge function, you can sort of use merge repeatedly to converge to a single state eventually, right? So that's the key idea behind mergeable replicated data types. So, and this notion we observe is actually sort of generalizes. This is the actual stuff in the second column here doesn't matter, but if you look at the first column, right? So there are several sort of data types for which you could define features, right? Which let you sort of reduce their merge semantics into set merge semantics, right? So therefore, sensible merge functions can be derived automatically for these data types, right? And we've also shown back then that all of these, if you actually use Git infrastructure to implement these data types, the performance you get is not that bad, right? We just straight away used Git library to implement the data types in programmatically, and the performance is sort of comparable, or it's sort of usable in practice, right? It's not that terrible, right? And this was covered back then on some of the tech press, for example, Hacker News and Coiler's blog, etc. But one key thing in the paper we published back then, the UPSLA paper, was we never actually discussed the theoretical guarantees of this mergeable replicated data types, right? We want the things to eventually converge, and that was the key intuition, right? So that's the key theoretical guarantee that we wanted MRDTs to support. But do they actually do that in practice? Well, we didn't have a proof back then. We just assumed it's a conjecture that they're going to converge. But in practice, you can actually have quite a complicated version graphs, which are not possible, which you don't actually do in GitHub, right? If you're working with your source code in Git, you might not manifest this sort of complicated graphs. For example, a graph is this, right? Where you have the first part is with the purple ones is something that we have seen before, a simple example. But then in the bug fix branch, you made a new commit, and in the merge, the feature branch, the previous commit was again committed, right? So eventually you sort of have this sort of a structure where you have crisscross, right? So you have what we call as a crisscross structure. So if you focus on this merge now and look at these two versions and go back and try to trace their common ancestor, the lowest common ancestor, you end up with two answers, right? So both the versions are actually lowest common ancestors for the merge that is going to happen there, right? So, but our abstraction of merge function relies on the assumption that there can only be a single LCA. How do you manage this conflict? How do you merge this, right? So before that, is this something that is even possible in Git, in actual GitHub? Well, turns out it is, right? So this is from my blog back in 2019. I've shown that an example of how the Git merge is inconsistent, right? So merge result seems to depend on not just what versions were merged, but also how they're merged. And second, the merge is unintuitive. You sort of, even when the successful merge, you do not necessarily have all the things that you expect it to have, right? So the auto merge there refers to Git's recursive merging strategy, where when you have two common ancestors, you just sort of merge them recursively, right? Okay, so I posted this on Hacker News, and I was thoroughly chastised because this is not something, I was told that this is not how you should actually use Git, right? Indeed, yes, maybe that is the case, but if you're trying to build a programming model on top of Git, we actually have to address these sort of questions, right? So how do we prevent this, right? So we can either constrain merge functions so that Git-style recursive merging is in fact safe, that is, it guarantees convergence. The other option is to constrain merchant graphs itself so that ill-formed graphs do not even never manifest, right? So we decided to focus on the second aspect first. We thought we'll come back to the first one. So yeah, so how do we manifest? So how do we constrain the graphs so that you would never have this problem, right? So the key intuition is whenever you're merging branches, let's say a pair of branches B and B prime, if you can ensure that the common ancestor for those branches and any other branches are causally related, right? Then you can actually preempt multiple common ancestors from ever manifesting. That's the intuition. So even more succinctly, if you can somehow make the graph a semi-lattice, right? If you can make sure that your graph always sort of has a semi-lattice structure, then there can only ever be a single common ancestor. So that's the intuition, right? So this is the intuition we actually sort of implemented. We proved, we actually manifested it as a distributed algorithm, right? So it's a fault-tolerant distributed algorithm that orchestrates well-formed distributions, executions of MRDTs. And this time we didn't take any chances. We actually proved convergence theorem, which says that regardless of how execution works, the execution always converges because the graphs are always semi-lattices, right? And it's also not that there's always a way so that you can actually merge these things and make progress, right? So we've sort of machine checked these proofs so that they are actually, the proofs are watertight and so on, right? And we implemented this in the distributed algorithm in a tool called Quark. And the performance results, the actual specifics are not important, but the key is that it actually scales quite well, right? So what's the key takeaway? So for any data type T, Quark lets programmers implement a diamond RSM for the data type T that is fault tolerant and scalable, and that is guaranteed to converge without needing a type-specific convergence proof, right? So that is the key aspect. So we do not force the programmers to actually write a convergence proof. Convergence is sort of built into how the executions are manifested by the distributed runtime, right? However, to our chagrin, convergence is not consensus, right? An eventually consistent replicated state machine is not a strongly consistent replicated state machine. Why? Well, convergence is about eventually agreeing on something. Consensus is about never disagreeing on something, right? So here, these two machines eventually agree on the final state while they transiently disagree, whereas these two machines never disagree on anything, right? So you want consensus in places where your data is critical. For example, let's say you're maintaining a banking account and the bank balance has to be strongly consistent because you cannot have diverging bank balances and sort of have double spending errors, right? So convergence is not consensus, and consensus needs to be is generally implemented separately from the convergence using the protocols that I mentioned earlier, right? So we'll now focus on the second aspect then. So for the cases where we actually need consensus, how do we make formal verification scale to the real implementations of consensus, right? So first of all, we look at why the consensus or verifying consensus protocols is hard in practice with help of a very, very simple example. So let's consider we have a 3-node distributed system, right? And let's say all of them are trying to elect a leader amongst themselves, right? So they do it by simple voting. So they vote for one of their peers, and if whoever gets the majority of votes, which is called a quorum, then that particular node actually wins the election, right? So let's say N1 requests vote from everyone, and N2 and N3 both vote for N1. So N1 now has list of votes that include both all three nodes. So N1 clearly has the majority here. So it's called a quorum. So it can declare itself to be a leader, and everyone updates the leader. So all of them are on the same page now. So we have a leader, right? A single leader for the entire system. So this is a form of consensus because the system is arriving at a consensus on who is the leader for this particular system, right? So this is a safe state because all of them agree on who the leader is. So conversely, let's say if we have a state wherein N3 believes that N2 is the leader, whereas everyone else believes that N1 is the leader, this is an unsafe state because we do not have consensus on the decision that we are trying to make, right? Okay, so the safety property is that for any two systems, any two nodes, if they believe someone to be a leader, those leaders better be the same thing, same node, right? See, easily stated, right? But how do we verify this in practice? So if you have an implementation of this simple leader election algorithm, how do we formally verify this particular safety property? Well, it turns out to actually verify this, you need a whole bunch of inductive invariants. So these are special properties. You do not have to actually understand exactly what these mean, but they sort of capture the key properties of the system, right? For example, whenever there is a leader message, whenever there's a leader message, there's only one of them. And whenever a node has voted, its has vote flag has been set, and so on and so forth, right? So they basically capture the key characteristics of the leader election algorithm that we have discussed so far, right? So that the inductive verification actually succeeds. The inductive proofs actually succeed, right? So compare this to the actual safety property that we have here, which is quite succinct, right? So the amount of invariance that one has to write even for this simple protocol to actually make the verification go through is quite a lot, right? So this is not scalable. This does not work for non-trivial implementations, right? And more importantly, so these systems, so these things, the invariants that I've written here, when we actually sort of represent them in a theorem provers and SMT solvers, etc., they have a quantification structure which are not amenable to automated verification. So you end up with your SMT solvers, your theorem provers timing out. So you have to write the manual proofs yourself, right? So inductive invariants, if they're the way that they are written, they actually induce undecidability. And undecidability introduces manual proofs. So this is a slide that I've taken from Nick's presentation. So this is earlier attempts at verifying realistic protocols, like real implementations of consensus protocols. For example, Raft ended up taking some 50,000 lines of code somewhere here. And Iron Fleet ended up taking 3.7 person years and so on, right? So these are real verification efforts in the wild that ended up taking multiple person years and tens of thousands of lines of proof, right? So clearly, this is not scalable, and we want to avoid this. How do we avoid this? Well, if you go back and look at all the invariants that we have written, the key thing in all of them is this thing called MSGS, which is basically a set of messages, right? So what we are effectively doing is reasoning about what the network contains. What message have we sent? What are we going to send? If there exists this message, then should this other message exist or not? And so on and so forth, right? So the complexity actually comes from the network, right? So network is the root of all complexity here, right? If only we can avoid thinking about network, maybe then we can sort of, much of the complexity will go away, right? So that's the intuition, right? So how do we sort of avoid reasoning about messages? Well, instead of a monolithic approach, where we try to build the strong RSMs on top of just straight away the low-level networks, how about we try a modular approach where we build the strong RSMs, or strongly consistent replicated state machines, on top of the weakly consistent replicated state machines, right? So how does this look like in practice? Well, if you go back and recall the abstraction offered by a weakly consistent replicated state machine, we have a replicated state across various nodes, which is sort of weakly consistent, meaning that changes sort of slowly propagate. So the best way to think about this is basically assume that you have sort of a blackboard. Let's say here there are 3 characters: Elmo, Cookie Monster, and Big Bird. Sorry? Big Bird, yeah. Trying to play a game. So they have a blackboard, right? So let's say they decide to divide the blackboard into various columns, right? So, and they try to play rock, paper, scissors, right? So simultaneously, Elmo might put on rock, Cookie Monster might put paper, the blue board might write scissors, and so on, right? So initially, only their updates are visible to them, but eventually everything starts visible to everyone else, right? And then they can sort of compute the results of the game to themselves. Right? So that's the key idea. So you have a system, you have a blackboard which is sort of eventually consistent. You can write things on it. Whatever you write is immediately visible to you. Whatever everyone else writes sort of becomes slowly visible to you, right? So think of this as an abstraction instead of messages and what you send on the network, right? Assume you have this abstraction. So the key question is, can you design a game using this abstraction so that you can solve the consensus problem, right? So for the simple example of the leader election, turns out, yeah, we can have a very simple algorithm. Let the blackboard denote a vote map where you're sort of mapping who voted to whom, for example, right? So let's say N1 initially voted to itself, N2 also voted to N1, and N3 voted to itself, right? Initially, only their own votes are visible, but eventually all the votes become visible to everyone else. So each node can compute the leader for themselves, right? So there is leader, because N1 has gotten a quorum of votes, N1 is the leader, and so is, that's the decision made everywhere. So you arrive at the safe state, right? So yeah, so observe that in this description of leader election, I've never referred to messages being passed by any of these systems, right? So I've never had to reason about what message was sent and when it was sent, right? So, and it's quite and in terms of cognitive overhead, this is easier to understand compared to the actual algorithm that we discussed a little while earlier. So we can sort of generalize it to have multiple rounds because a leader election might fail in a single round, right? And you can further generalize it from not just for the leader election, but rather to arrive at consensus on any decision, right? So like propose something, who has proposed it and what is the proposal and so on, right? So this ends up being just Paxos, right? So you can straightforwardly arrive at Paxos from leader election simply by generalizing it for multiple rounds and for various kinds of proposal types, right? So this version sort of is a little bit simpler than the simpler version that the Lamport presented back in 2001. So this is I presented it at VDS conference in Morocco a few months ago. So Mark Shapiro is one of the legends in distributed computing. So this is what he has mailed me at the end of the day. So said, thank you, I finally understand Paxos because this was much easier to understand, right? So yeah, so this is cognitively, this is much easier to understand. But what about formal verification? Well, whatever is easy on human cognition is also easy on machine cognition, right? So we have developed an entirely new way of reasoning about consensus, like verifying consensus under this abstraction, right? So we have a new proof theory that uses something called update preconditions, a name that Nick has come up with, instead of inductive invariance to do the verification. And it so turns out that this way of doing things is friendly to automatic theorem provers, right? So it does not introduce additional quantifier alternations that do not already exist in the protocol logic, right? So with that, we were able to actually verify a realistic implementation of the Raft protocol in around 400 lines of code. So well, it was smaller because most of the logic of replication, etc., was handled by an underlying diamond RSM, which we have verified separately. Specification is just 100 lines of code, no quantifier alternation. So the entire thing, the actual implementation was completely automatically verified by an automatic theorem prover, right? And not only that, the verified implementation performs competitively with HCD Raft, which happens to be the actual industry standard Raft implementation deployed in production in many systems, right? So this is something that's coming up in a few months in Uppsala, right? Okay, so this is the results I have with respect to the first aspect of my talk. The future work here will focus on essentially removing the overhead of message complexity in the diamond RSM abstraction. So maybe that's a talk for a different day, right? Coming to point number 2, right? So beyond scalability, the other sort of impediment is generality, right? As I mentioned, formal verification in distributed systems primarily focused on safety aspects, but there are systems that need verification that needs security or privacy guarantees to be verified, right? So as an example, so this is a work that I've done with Kirby, with collaborating with Eric, right? So here is an example, right? So let's say we have a simple decentralized chat application. There are three people, A, B, and C, talking amongst themselves. Let's say A sends a message to B and C, and when the message is sent out and the network is open, so there can be adversaries or attackers sort of waiting on the network, right? So to an outside adversary, the two messages should look identical or indistinguishable, as we call it, right? But in general, they are not, because if they are in plain text, then you can easily distinguish between first one and second one. Well, the easiest solution is just use encryption. So we sort of encrypt these things and say now, the adversary cannot distinguish between A and B, so we are good, right? Well, not so fast, because it turns out that even with encryption, right, there is the control flow can manifest in a way wherein you can sort of the adversary can be able to tell or distinguish between two separate things, even which is otherwise not possible, right? So I'll motivate and I'll sort of give you an example of that, right? So there is one-time pad encryption is sort of a standard encryption or sort of easiest encryption algorithm in cryptography. So all it does is basically exclusive ORing with a specific key, right? So you have a key that is generated, which is of the same length as the message. You XOR it, you get an encrypted message. Then you XOR with the same key, then you get the message back, right? Why? Well, because XOR is self-canceling. So A XOR B is A, right? So as simple as that. So this is called a one-time pad encryption, and this is OTP encryption is perfectly secure, meaning that if the key is random, then the resultant encryption, the encrypted version, looks random to any attacker, right? Okay. So, but what happens if we reuse the key, right? So there are two messages, message 1 and message 2. You have encrypted message 1 and encrypted message 2. So you have two encrypted messages visible to the attacker. The attacker can simply XOR them, right? So XOR is self-canceling, so you sort of cancel both of these things. So attacker ends up with plain text message 1 XORed with plain text message 2, and therefore they can learn which bits of message 1 and message 2 actually differ, right? So it is no longer indistinguishable from random. You can actually learn some information from this thing, right? Just because you've reused a key, right? This is a very simple example, but these sort of things do happen. In the real encryption primitives actually have this arguments called nonces, and reusing nonces or sort of using them in a predictable way can lead to you leaking certain bit of information that is otherwise not leaked, right? Or not supposed to be leaked. Right? So in an ideal case, we want this scenario wherein you send a real message 1 and real message 2, and a random message 1 and random message 2. You want these two scenarios to be identical to the attacker. But it so turns out that the attacker, in this case with the one-time pad encryption, can distinguish between these two scenarios and also between these two network traces, right? So if you have a verification engine or a reasoning engine, that should be able to distinguish between these two cases and tell you that, hey, this is unsafe, right? But if you actually plug in the standard models of cryptography, the symbolic model of cryptography, right? So I'll come back and discuss these things, but the bottom line is it actually is imprecise to detect this sort of an error, right? So it tells you that the implementation of OTP that you have is actually safe, right? Why? Because in the symbolic model of cryptography, to enable automated reasoning, all the plain text and ciphertext are considered uninterpreted symbols. The only way to get a plain text back from a ciphertext is by using a key, right? So otherwise, the ciphertext is indistinguishable from the other ciphertext. The only way to distinguish two ciphertexts is if one can be used to deduce something that the other cannot be used to, and that's not possible here. And therefore, it's not, the two OTP encryptions are said to be, or these two scenarios that I've shown here are deemed to be indistinguishable, right? And so the proof goes through, which is bad, right? It shouldn't have. So how do we fix this? Well, in our Roopstar 23 paper, we came up with this new probabilistic model of cryptography, right? So the idea is, let's not treat these things as opaque symbols, but let's sort of write them, model them, the cryptographic primitives as basically functions that sample bit strings from well-defined distributions, right? For example, if you have a perfect cipher, right? It is simply returns a randomly sampled string from a uniform distribution. But if a perfect cipher with of length L, it might sort of only get or only sample from a distributions of length L, for example, right? Or you can XOR it with a nonce and so on. So there is multiple ways in which you can axiomatize the cryptographic primitives using probabilistic abstractions that you cannot do using just symbolic abstractions, right? So we can now reason about symbolic probability of generating a trace. So when you have two encrypted traces, they are indistinguishable if and only if they are equally likely to have been generated by a protocol execution. Stated otherwise, two protocol executions are indistinguishable if they are equally likely to generate any random trace, tau, right? So this is the verification condition that we have to verify for a given protocol. So there is a logic called probabilistic relational Hoare logic, which we adapted to this situation to actually do that. So when we implemented a tool called Waldo, which is embedded in this automated reasoning framework called F-star. So using Waldo, we were able to find sort of some gaps or sort of under specifications in the Raft specification of TLS Encrypted Client Hello extension, right? So I'll give you a brief description of what that actually means. So TLS is a protocol that everyone uses to implement HTTPS, right? So it is the transport layer security protocol. So TLS, the job of TLS is to establish a secure communication channel between you and the server, right? So TLS has an initial handshake phase wherein the server name is actually visible, right? So because this happens in plain text, but once server and client exchange the keys, then the rest of the communication happens in encrypted text, right? So this is great, but the problem with this is sensors take advantage of this to block connections to certain server names, right? So for example, a sensor might block your connection to twitter.com, right? So the TLS standards committee has come up with an extension called ECH, Encrypted Client Hello, that sort of introduces this additional indirection through a proxy, right? A well-defined proxy, so that even your server name can also be sort of encrypted, and the proxy is the one sort of that decrypts it and routes your request to appropriate server, right? So the idea is, since the sensor sits here, they should never be able to tell the difference between when you're contacting, let's say, twitter.com or google.com, right? That's the intention. So, but is it? So turns out sensors can actually block even ECH connections. In other words, there is, even the encrypted client hello extension, you can manifest network traces for two different servers that are distinguishable, right? So the reason for that is there is a certain underspecification in the draft in the ECH, which lets you sort of scramble a few cipher texts or cipher suites, and with the different implementations choosing different options, you end up having distinguishable implementations, right? So we were able to find this using Waldo and suggested sort of 4 fixes to the standard, which were actually adopted. I mean, 2 of them were already known and 2 of them were adopted by the ECH standard. Okay, so that's the Waldo or the security work. The third thrust that I've been working on is basically improving the usability of the formal methods or formal verification with respect to the distributed systems, right? So this is the work I've been doing with my students, Nick and Christian, Sean, and also with collaboration with Evan. So several tools have been developed in this work. So I'm primarily going to talk about the Historia and Disprove briefly, right? Okay, so what are the artifacts of formal verification? Well, you have listened to me so far. You've seen I speak multiple times about specifications, invariants, and proofs, right? So of these 3 artifacts, so more often than not, specifications are sort of intuitively known to the programmer. And if not, they can actually be recovered from the other statements in the program, right? So if we have this, so this is a simple sort of definition of the leader election protocol in a language called P, which is used at AWS. Don't worry about the actual definition of all of these things, just focus on the assert statement here, right? So the assert statement sort of tells you that when a leader is being declared, it should be the case that I don't already have a leader, or if I have a leader, that leader better be same as the leader that I have that is being elected now, right? So from this, you can recover the safety specification that I've shown before. So it's easy, right? Coming to proofs, if we can somehow encode specifications and invariants in decidable logic, then proofs can be sort of automated as well, most often. So the key question is, what do we do about invariants, right? So invariants are notoriously hard to discern and quantified invariant inference is still an open problem, right? So as I've shown with the leader election example, right? So the question is it possible to circumvent the need for invariance, explicit invariance? So it is the dream for many formal verification folks. So yeah, the question is, can we do that, right? So if you think about that, an inductive invariant sort of characterizes every reachable state of the system, right? So the way we do formal verification is by characterizing every reachable state of the system through an inductive invariant and showing that that does not overlap with bad states, right? But how about what if we reason about unreachable states instead? What do I mean by that, right? So in a regular forward verification, you have initial state and then a set of reachable states, right? You write an inductive invariant that sort of covers the reachable states and maybe some more states, right? And show that this entire thing is all states reachable are from the initial state are basically safe, right? So reason about all the states regardless of what the actual property you're trying to verify, right? But if you try to think backwards, right? You start from an unsafe state, right? And try to work your way backwards to the initial state, right? You try to find a path from the unsafe state from the initial state, and if you can find such a path, then clearly the program is incorrect, right? So if you let's say if you have tried multiple paths, and if you've sort of in all the paths you've encountered a contradiction, right? That effectively means that your initial state cannot reach the unsafe state, right? So this is effectively the backwards verification. We start from an unsafe and then work your way backwards. So we've sort of tried this approach. So this is an UPSLA 23 paper from Sean, with Sean, Sergio, and Evan. So we've shown that this sort of backwards interpretation or backwards verification sort of works in a bunch of Android applications. We built a tool called Historia. And then we decided, okay, this is an approach that can also sort of work for distributed systems. So we've sort of transplanted this approach to the specifications of distributed protocols. So it adapts. So we built a tool called Disprove that sort of adapts the goal-directed formal verification to distributed protocols. So the key thing that Disprove was able to achieve is without explicitly provided invariance, right? It was able to actually prove the safety of the leader election protocol that I've shown before, right? It didn't even require the update precondition that we have talked about. No invariants were needed. Just the safety specification was sufficient to show the unrealizability of error state, right? And it also is guaranteed to terminate on algorithms composed of affine actors, that is the actors that sort of do a specific set of communications, right? So the key bottleneck here is computational complexity. So so far we are not able to scale this approach to larger distributed protocols, and that is a work for for future work, right? Yeah. So with that, I'd like to conclude. So the conclusion is programming distributed systems is hard due to the sheer combinatorial complexity of so many things that can go wrong. Formal verification can help fail-safe operation and resilience to adversarial attacks, but there are several impediments that I have discussed, which is basically the poor scalability, the insufficient generality, and also the steep learning curve associated with formal methods. So my research sort of addresses these impediments by developing novel programming abstractions and automated reasoning techniques. The goal is to make probably safe distributed systems development accessible to mainstream application developers, right? So all the research has been published in open access journals and is available as open source, implemented in open source tools, right? And I'd like to thank funding agencies who have supported my work. Thank you. Yes.
I wanted to know if these kind of systems are applied to cloud or data.
So you mean the formal verification applied to cloud? Yes. So the applications that I've talked about earlier, so MRDTs, for example, are a programming abstraction to design applications for cloud, right? So the verification, I mean, I had previous work that I haven't covered today that verifies the cloud style applications specifically, that basically tries to do bounded verification on cloud and so on. Yes, it is possible. The short answer is yes. Yes, Sriram.
This is synchronization mechanisms in your talk. So how do you get away from reasoning about things like rendezvous and all of those crazy things that you have to reason with at the lower level?
Could you explain? Could you elaborate a rendezvous source, for example?
Messages.
Yes.
And so then you get into things like which order, like reasoning about causality. Right?
Exactly.
And so how do you get away from it?
So if you let's dissect that question, right? So you talked about causality of messages and so on, right? So, but that as an abstraction is not directly relevant to your consensus algorithm and so on. If we can somehow abstract the message communication behind a causally consistent layer, right? Then you have a modular approach. The problem doesn't go away. There is no free lunch. You have a separate abstraction, which is diamond RSM, for example, wherein you're now dealing with those problems there, right? So you're trying to prove your causally consistent message delivery at that layer. So just to add practical data to that question, so there have been several libraries that actually do verify causality of messages, causal consistency of message delivery. Separately, the way distributed systems have been built so far does not make use of those things, right? Because they are essentially building everything from scratch every time. So this is a way of essentially doing things modularly so that you sort of offload that verification problem to someone else, effectively.
So as a follow-up, have you tried anything about like monitoring something in runtime that makes your verification easier? Is that sort of approach possible in your work?
So the first work that I talked about, Quark, it is a runtime approach that makes verification easier, some say. It is sort of an extreme example of that because it eliminates the need for verification, static verification, because convergence is guaranteed by the runtime itself by orchestrating how the version graphs manifest. So there could be less extreme cases. We haven't explored them yet. Yes, Tom.
Great talk. I'm very interested to learn the consistent convergence versus consensus. And
Yes.
you did a great job. Can you help me out by clarifying? Are you proposing consensus as a better alternative, or is it an alternative? If so, can you help me understand the pros and cons consensus versus convergence?
That's a great question. So from the formal verification standpoint, I do not advocate for either consensus or convergence, right? So it is something that is a decision that needs to be made by the application developer, right? It could be the case that your data may not need to be strongly consistent all the time. For example, the example that I briefly mentioned was YouTube view counter, right? It's okay to see diverging views as long as they eventually converge to the same value, right? But there could be cases where you actually want strongly consistent data. In those cases, you have no option but to use consensus. And so this work was about when you have no option but to use consensus, how do you do it in the most effective way?
Just follow up on that.
Yeah.
So you started with Amazon, Instagram, and Bitcoin. How would you recommend them? Just curious. Which one is more consensus?
Oh.
Studies this.
So I had, let's take Amazon, let's take Bitcoin first, because so what we have in Bitcoin is, to actually commit a transaction, there is a consensus, but the Bitcoin's consensus is based on rate throttling, so the proof of work and proof of stake, those things. So they do not actually fall under the conventional consensus that I've talked about, but it is based on consensus, right? Whereas the other, so in Amazon, for example, so S3 lock service, there is a lock service within S3 that is actually a consensus service, right? And they actually use, I mean, from what I've known, they haven't published the data, but from hearsay, they've actually modeled it first in TLS, then in P, and eventually verified or model checked it, and before they actually implemented the consensus algorithm. Instagram, I have no data. I would assume that the username creation may be a strongly consistent operation, perhaps. I don't know.
You have any questions online?
Yeah, thank you. Thank you.
Okay, so I think this is the time. We have more questions we could ask maybe after.
Yeah.
So let's thank other speaker.